Right. Good afternoon. Good morning, everyone. Welcome to our fourth and final Future Faculty Seminar Series. I'm Jessica Wilson. I'm chair of the Student and Postdoc Services Committee for AEESP, and I'll be co-hosting this seminar with Mohan Chin. We have two excellent presentations today, each about 25 minutes, and then we'll have about 5 minutes afterwards for questions. If you're interested in connecting via social media with AEESP, you can scan the QR code to see the LinkedIn group, and then also they are on Blue Sky, which is another social media network. So I'll put this slide up at the very end for those of you who want to scan and join. But for now, I will turn it over to Mohan, who will introduce our first speaker.
Thank you so much, Jessica. So Yuxian, you can try to share your screen, and I will give a brief introduction of you. Okay. So Yuxian is currently a postdoc at Rice University in Xilin's group, and prior to that, he got his PhD in environmental engineering from AEESP group at Columbia University. And his talk today is about advancing selectivities of ion exchange membranes for water, energy, and the environment. So please feel free to get started when you are ready.
Thank you, President. Thank you. Sorry, one more question again. Are you seeing the slides correctly?
Yes.
Okay, great. Yeah, thank you, President, for the warm introduction. Hello, everyone. Yeah, very happy to be here. I see a lot of familiar names in the list. Before jumping to my research, a little bit background of myself. Yeah, I did my undergraduate study in Hong Kong in and my BE degree in 2017. After that, I moved to Columbia University, which is in New York City, where I got my master's degree in 2019 and a PhD degree in 2024, both in environmental engineering. So since then, I flew south to Texas at Rice University to work as a postdoc. Very happy to have this golden and wonderful chance to share my past, current, and research and a little bit about the future research interest. Going to do. I tuned my title a little bit to better reflect my focus on my research, which is on the electromembrane technologies. I want to advance this to better enable the circular economy of water and critical resources. Doing so largely dependent on separation technologies, especially selective ion separations, which has many significance. For example, desalination, which refers to separating our salt ions from the saline feed so that we can produce fresh water to combat water scarcity. Also, in the wastewaters, there are many nutrient ions which we can recover and beneficial residues and fertilizers. Another typical example is critical minerals, which is very hot in recent days. This is very essential for our transition to green energy economy. For example, the lithium extraction from the unconventional sources. Among the different separation technologies, here I'm focusing on our electromembrane process, which offers a promising avenue. By its name, we can tell that electromembrane has two parts, electro and membrane. For the membrane part here, it's usually called ion exchange membranes. These membranes are a charged thin film of charged polymeric thin films. They allow the passage of the ionic species that has opposite charge sign to the membrane itself, while we pair the ions with the same charge sign. Electro driving force here are directly on the ionic species for their transport or the reactions. We will mention both of them later. This is very compatible with renewable energies nowadays. Some typical applications of electromembrane processes, for example, brackish water desalination by electrodialysis, flow battery or salinity battery for energy storage or conversion, and also chemical production like the chloroalkane process. They can easily feel that in all these electromembrane process, the membrane parts are the key components to achieve the separation selectivity. And further in that, actually, there are different types of selectivity in these ion exchange membranes. The most fundamental one is the separation between counter and co-ions. Here, counter ion has the charge sign opposite to the membrane itself, while co-ion has the charge sign same to identical to the membrane itself. This is also called permittivity. This has been well established in past many years. Later, among the counter ion group, we want to separate ions with different valences. We call them valence selectivity. And commercial membranes with relatively good valence selectivity already available in recent years. However, if we're moving forward, what if we want to separate counter ions with the same valence? They are more similar and for sure more challenging. And unfortunately, commercial products are not available at this moment. In addition to ion-ion separations, there are also separation between ions and the neutral species. For example, the water molecule most commonly used solvent electromembrane processes. Unfortunately, the study here is also, this part is also under study. So putting this together, exchange the membranes with advanced selectivity, they are still critically lacking. So to address this part, this is the focus of my past research, where I followed this roadmap or strategy, which is by diving deeper into the fundamental mechanism to give us insights from which we can learn how to fabricate and develop ion selective membranes. So here I like to use two projects in my PhD research as a demonstration. In the first project, I studied the permeation behaviors of ions in charged membrane matrix. For ions to transport across the membrane, there are two important factors. First is how many ions in the membrane, their concentration, and then how fast they can move in the membrane, which is about the diffusivity or mobility in the membrane matrix. For the first question, how many ions in the membrane, the established donor-Manning model can work well. They can really capture the ion concentration and absorption behavior as well. However, they have a big disadvantage that, a big deficiency that in this model, they separate the counter ions into two parts. For the portion of counter ion closer to the fixed charge group in the membrane, they are called condensed counter ion. For the rest counter ion further away, they are called uncondensed counter ion. But in this model, they are assuming that these condensed counter ions, they are immobile. This is really a big portion of the charge carriers in the membrane matrix. But they are really, if they are really just doing nothing even on the electric field, not surprisingly, we're going to largely under-predict the ionic conductivity of unchanged membranes by using this current model. So to address this issue, I proposed an analytical equation to describe the mobility of condensed counter ion in this case. Which is here, I will not talk about too much details of this equation, but if you're interested with that, we can definitely chat more later. After putting this equation back to that into the donor-Manning model, we can achieve reasonable prediction of exchange membrane ionic conductivity across a wide range of electrolyte solutions, which is very good. Further on that, if we on this modified model, more complete model, we can dig out more important insights or implications on existing membranes limitations on the ion selectivity. We learned that for the ion mobility, how fast they can move in the membrane, they're mostly determined by two important factors. One is electrostatic factor, the other one is spatial factor. But if we want to separate counter ions with the same valence, their electrostatic effect will be pretty much the same because they have the same charge. And their spatial term will also be very similar. So in other words, that is to say, their relative mobility in the membrane matrix will not be that different. That means, in other words, this how fast it can move with the membrane could not give us sufficient separation results. So, so that means to enhance the membrane selectivity, we need to instead focus on how many ions can be present in the membrane matrix. If we can have high concentration of target ion in the membrane, there are more chances we can get better selectivity toward that target ion. So to verify this understanding, I apply this idea to help me fabricating membranes targeted for separating alkaline metal ions. These ions, they have the same charge, +1 charge, and they have the very similar hydrated ion size, so very challenging to separate them. Because charge separation or the size separation gonna be not easy to carry out. But these membranes, the ions are not very similar everywhere. They have larger difference in their bare ion radius, which will give them different charge density. For example, in the bulk solution, lithium ion, due to its higher charge density than the potassium ion, it will track more hydration waters inside the hydration shell and also more tightly to attract its hydration waters. This can be reflected by the much larger difference in the hydration-free energy. We can see here, lithium ion has much higher hydration-free energy than the potassium ion. So it's good to see the larger differences because that means chances for us to achieve separations. So how do we make use of that? Here, suppose we have the both cations present in the bulk solution, and they will all want to move into another water pool media. But during this process, they all need to lose part of their hydration waters just simply because there's no sufficient water molecule inside this media to keep all of them fully hydrated. As potassium ion has lower hydration free energy, it's easier for this guy to lose part of the hydration water and go into the media. However, this process will be more difficult for lithium ion due to the larger energy penalty arises from the higher hydration free energy. So here we will see that one selectivity can be observed at this step. And we hypothesize that such a process can also be applied to exchange membranes to uptake the ions with low hydration free energy, provided that the membrane matrix itself is sufficiently waterproof. However, for many commercial membranes nowadays, they are usually highly water swollen. So in order for this partial dehydration phenomenon to be important in the membrane, we need to squeeze out a lot of the water from the membrane. That means to develop membranes with watery environments. And also, we adopted a polystyrene as a polymer backbone, which allows fast cell fabrication and modification. Polystyrene itself is very hydrophobic, and then we introduce a small amount of the softener groups. It's first to give us fixed charges and also only introduce a little bit amount of water. By changing the softenation level, which means fraction of the polystyrene unit to carry softener groups, we can easily tune the membrane water environments. This is reflected by the number of water molecules per fixed charge, denoted as lambda here. You can see by going to lower softenation level, we can make the lambda value quite small. Next, we challenge this membrane in the electric field during transport. Here on the left-hand side, we have the mixture of ions. Both cations are present, and they will also all want to transport across the membrane under the electric field. We measure the ion flux, and the relative flux normalized by the concentration ratio. In the field side is denoted as transport selectivity. Here we plotted this potassium over lithium transport selectivity as a function of the water per charge site. So firstly, we can see that all our membranes prefer proton transport over the lithium ion. The potassium ion transport over the lithium ion, and the selectivity goes up when lambda values goes lower. So it generally agrees with our expectations. To have further understanding how this selectivity, where does this selectivity come from, we decompose this transport selectivity into two parts, which corresponds to the two steps for ion to transport across the membrane. The first step, it happens at the membrane solution interface, because ion need to first partition or go into the membrane. We will see a selectivity at this step. We call this sorption selectivity or the partition selectivity. Then, when in the membrane matrix, ions will need to migrate downward the membrane thickness under drawing forces, and their relative mobility will give us mobility selectivity. And the product of the two steps, sorption and mobility selectivity, can give us approximately the overall ion transport selectivity. So next, we characterized the potassium over lithium sorption selectivity, and again, as a function of the different membrane water environments. All these membranes, they prefer the sorption of the potassium ion than lithium ion. And also this selectivity increases when the membrane gets more waterproof. This directly supports our hypothesis. On the other hand, about the mobility selectivity, it still shows that potassium ion moves faster than lithium ion, but this is generally insensitive to a change of membrane water environment here. So putting this together, we can see that both the sorption step and the mobility step, they contribute to the overall transport behaviors across the membrane. But sorption step for sure contributes more than it, showing that the preferred potassium transport through our membranes is primarily driven by the selective partitioning behaviors. Also, the influence of the changing membrane water environment is also through the sorption step to affect the overall transport selectivity. Okay, to quick summary of the two projects I just covered. From the fundamental transport insights, we learned that we need to enhance the target ion presence in our membrane. So to achieve this, we developed waterproof membrane matrix to leverage the difference in hydration-free energy. And our membranes demonstrated that there is increasing selective transport of the potassium ion over lithium ion when the membrane gets more water poor, and this is primarily driven by the selective partitioning behaviors. Later in my postdoc research, I further expanded my strategy or roadmap to include another important electromembrane, which is called a bipolar membrane. This guy has a very interesting structure. It's a laminated structure, like a sandwich. On the two sides, there are two polymeric layers. One of them carry negative charges, we call them cation exchange layer. The other one carries positive charge, we call them ion exchange layers. They're essentially exchange membrane we have just mentioned in the previous slides. For the stuff they sandwiched in between, it's a thin layer of catalyst, which are supposed to carry weak ionic groups like the carboxylate group, ionic group, or amine groups. Here I'm showing the SEM image of the atomic particle as an example. The most interesting behavior of this bipolar membrane is that when we apply electric field across it, water molecule will be polarized inside the catalyst layer and finally dissociates into protons and hydroxide ions. So here essentially we are converting electricity to chemical potential energy. That means using bipolar membrane allows us to have an electrified approach to change the pH conditions on the two sides of the membrane. In addition to that, as the membrane process still have the ion separation capabilities because of the two polymeric layers. These unique features have making bipolar membranes very attractive to anywhere we want to play with the pH conditions. For example, the water treatment to kick out the contaminants, water electrolyzer, produce hydrogen gas, or the CO2 capture. However, the broader deployments of the bipolar membranes are still experiencing hindrance. A large portion of the reason comes from the water dissociation parts. The kinetics are still not satisfactory enough. So to have a better kinetics, naturally we are thinking of the better catalyst array. And this is indeed the focus of many researchers in the past decades. To design better catalysts, we need to know what is happening in this catalyst layer. This layer is really very thin with a typical thickness of 100 or several hundred nanometers. Regarding how the water dissociation happens in this catalyst matrix here, there have been different mechanisms proposed by past researchers. For example, if we have the hydroxide group as a catalytic site, some people proposed a deprotonation and deprotonation process. But another group of researchers argue that the reactions don't happen at one location. There will be proton hopping involved and also other different mechanisms now shown here. Among all of them, one of the key steps is proton transport mediated by the surface, catalytic surfaces. So it's important for us to have a deep understanding of such transport behaviors. Also need to have in mind that this transport happens at a very special local physical chemical environments, like electric field. They come to a surface with different angle and strength is for sure an important factor. But today I will not talk about this part, but focusing on another important factor, which is called nano confinement. So what is this? In the catalyst layer of bipolar membrane, the catalytic particles are usually closely packed, which means the catalytic surface, they are not directly open to the bulk water. Instead, we are experiencing different degrees of restriction. When the restriction comes to the nanometer scale, they are called nano confinements. Under such cases, the water structure and the other dynamic behaviors may be altered, which will subsequently affect the proton transport behaviors, which is what we want to look at here. However, as the targeted system is so small, nanometer scale, it's going to be very challenging if we use conventional experimental methodologies. So here we turned to simulation methodologies. And across a wide spectrum of different simulations, we used the bottom left guy, which has the smallest time and length scale. This is because our target system is so small. Essentially, we're using density functional theory and ab initio molecular dynamics to probe the molecular behaviors in the catalyst layer. And for the targeted system, we used the anodized titanium dioxide nanoparticle for their demonstrated performance in previous experimental studies of bipolar membranes. Here I'd like to briefly introduce how we constructed our model system to carry out a simulation process. Using density functional theory, we brought the two TiO2 surfaces quite close to each other. By changing the distance here, we can control the degree of nano confinement. We're then adding a few water molecules to hydrolyze the surface, which actually give every surface titanium side one hydroxyl group. This agrees with past simulation studies and also supports the proposed mechanism we just mentioned. Then we add in a few free water molecules. Here, by changing the distance here from 6 to 10 angstroms, we can change how the amount of free water molecules can be captured inside this confined space. But I will not talk about the more details of simulation process for the sake of time. If you are interested, we can definitely chat more after my talk. So this is the proton transport process we're interested in. This essentially has two steps. Here, this big scenario is that one water molecule to bridge the two nearby surface hydroxyl group by hydrogen bonding. First, this proton leaves the surface, go to transport to the nearby water molecule, forming a hydronium ion. We calculated the free energy of activation, which essentially is the energy barrier and the function of different confinement distance, which we found that indeed this distance has a strong effect on the transport kinetics. Starting from the 10 angstrom distance, if we're going to squeeze the distance down, the energy barrier is going to first increase and then largely decrease. For this trend, this still hold as a next step transport where the positive charge goes back to the surface, but another hydroxyl group, again by the switch of the hydrogen bonding, still we saw this trend. And interestingly, when we have appropriate nano confined distance here, we may largely reduce energy barrier and may even make the proton transport process barrierless. This information can be very important for us to design or engineer the catalytic surfaces and the geometries to making the water dissociation process more efficient. Further, water structure analysis tells us that this trend is probably due to the changing of the hydrogen bonding network among the water molecules and with the surface hydroxyl group. Okay, so quick summary of the three projects representative of my past and current research. They all follow the idea that using the fundamental insights to design better electromembranes. For example, having the fundamental transport insights help us to design better unselective membranes, and better understanding into the molecular behaviors in the catalyst surfaces can also help us design better catalysts to enable more efficient bipolar membrane operations. Building on all this knowledge and the skills I got so far, I'd like to expand my interest to contribute to the circular economy of water and critical resources. I guess many of us have heard this term of circular economy quite a few times. This is different from the conventional linear economy, in which we produce product, use it, and dispose it. Circular economy requires us to recover the resources from the waste for beneficial reuses, which is for sure more sustainable. Here I'm interested in wastewater or waste streams where we can extract out water, critical minerals, and nutrient ions for different but all very important reuse purposes. But one big challenge is that here this source water is the water chemistry is very complex and with highly variable components. For example, the very high analytical strengths or very harsh chemical conditions. So to address this challenge, for sure, bipolar membrane can offer a promising avenue, but still some gaps to be filled, which I am planning to tackle in my future research through interconnected research thrust. First one is to having deep understanding the transport mechanism in electromembrane process, but this time facing into more complex and practical chemistries. When the membrane faces relatively dilute and also simple solution, the transport understanding is quite well established, but it's still not enough when we are facing more complex chemistries. This insufficient understanding actually are impeding us to designing better membranes to allow the customized selectivity to certain ionic species. And also I want to have the big membrane have acceptable level of permeability to mitigate this well-known trade-off between permeability and selectivity in many membrane transport processes. After having the membrane to be functional, we need to put them into the device level. So to connect the material property to the process level performance to establish a multi-scale models and to evaluate the performance of the different electron membrane technologies. So that ends all my story today. With that, I will thank so many people. Firstly, my advisors, PhD advisor, Dr. Ip, postdoc advisor, Dr. Lee, Dr. Sefley, and Dr. Vadusco for their continued guidance and help. Also, I want to thank my collaborators, colleagues, and their members in Columbia University and Rice University. I want to thank my financial support from SUS program of Columbia University and the Rice Water Institute. Really appreciate this wonderful platform from the AEESP to share my research. And for sure, thank you for your time and attention. Now I'm very happy to take your questions and comments if I still have the time. Yeah, thank you.
Yeah, thank you so much, Yuxuan. Any questions? You can just unmute yourself and then ask.
I'll start with a question if nobody else has one. Great talk. This really outside my area of expertise. So I think maybe this is like a more basic question or something that has been answered. But I think my question is about membrane uniformity and membrane fabrication for your sulfonated polystyrene membranes. Mm-hmm. So can you just like briefly talk about that fabrication and if you observed any like variations in the sulfonation or hydration across those membranes and how you accounted for that?
Oh yeah, it's thanks for mentioning this because for second I skip a lot of these parts. Here, so we worked with some collaborators from the chemical engineering at Columbia University to make this membrane, and there's polymer material expertise. They suggest us to using the polystyrene. They said it's a model system, very allows facial fabrication, easy for to satisfy our needs, and so we used a very simple reaction, which is basically soaking this, for the polystyrene polymer. It's actually in the, I think it's concentrated sulfuric acid and also acetic acid as a mixture as a sulfonation agent to introduce sulfonate groups to the polymer. But we carefully controlled, we only introduce a small fraction of the sulfonate group here, which means control X to be quite small. But it also have some challenges with too small. The material is going to be very brittle. It's not permeable. But there's too many X here, too high X here. And too many sulfonate groups, they are very hydrophilic. They attract a lot of water inside. Then the polymer is very, they will gradually just dissolve in water. Yeah, that's some of the challenges we encountered here regarding how we tried a lot of ways to control the different sulfonation degrees here.
Yeah, thank you.
Thank you for your question. Thank you.
I think I have a very simple question here. So, Yuxian, why do you care about lithium potassium selectivity? Are there any specific streams that has pretty high concentrations of potassium there together with lithium?
Oh yeah, so our primary idea of using this pair is for sure we want to separate our lithium ion because some unconventional sources still some point of some research streams to separate our lithium ion. That is our target, and for usually they are coexisting with potassium ion. Also for their similar properties, is very commonly used in this kind of studies. That's a primary driving force here, and but different from what we may usually think is that this membrane is not preferentially transport lithium, actually preferentially transport the potassium ion for the mechanism of the dehydration I mentioned in my talk, and then the lithium ion should be more retained at this site. Still, doing so can allow us to achieve separation. But I would say still, it's more like a fundamental part study, to be really into a meaningful separation. For example, so electrodialysis will have to have more steps to go.
Okay, thank you so much.
Thank you.
Jessica, I think I'll hand this to you for the second talk.
May I ask a question?
Oh, sorry. Please.
Sure,
no.
yeah.
Thank you, Dr. Huang. My name is Daniel Talbot, and got connected through different consortiums, but really like this topic quite a bit, and just finished my master's thesis in monovalent selective electrodialysis and continuing PhD work in it. I guess I was very curious, and I know Yip's work as well, so I recognize those slides. I was curious, as it relates to the selectivity transports that you tested, did you try it out with the monovalent, divalent? I work a lot with brackish water, so I'm interested in the preferential removal of sodium relative to calcium and magnesium. So I'm wondering if you tested with other species, and also, do you have a forthcoming publication on this, or if not already, because I'd love to read it further.
Yes, thanks for mentioning this. Very good point. And indeed, we are for the membrane, we try to do some preliminary experiments using the membrane to separate, for example, lithium ion and magnesium ion. Unfortunately, the selectivity is here not good. It's a 1-2 or something. Yeah. What we are thinking is that it's actually because in the membrane the fixed charge concentration is very high, which gives a very large donor potential between the membrane and the solution interface. This is more favorable for the partition of the divalent ions magnesium because it has a higher charge. Yeah. Then those say, this is not good. It's focused on the mono ions selectivity separation. Yeah. And that's basically what we observed. Yeah. Thank you for your question.
Okay.
Thank you.
Sounds good. We're still working on it then.
Good luck.
Yeah.
All right. Well, please join me in thanking Dr. Huang again for a great talk.
Thank you.
I'm pleased to introduce our next speaker, Anja Davidson Ralston. So you can feel free to share your slides now. Anja is a postdoctoral fellow at the King Center on Global Development at Stanford University. And prior to joining Stanford, she earned her PhD in environmental engineering from the University of California, Los Angeles. And today she will be talking about leveraging nature-based solutions to mitigate the environmental health impacts of wildfire. So thank you, Anja.
Thank you, Dr. Wilson, for this presentation. So thank you for the introduction. I actually did my PhD at UCLA in environmental engineering. I have a bachelor and a master in civil engineering in France from ESTP Paris, and did a master and PhD at UCLA in environmental engineering. And now I'm in the Stanford School of Medicine in Professor Joseph Andrew Lab in infectious disease. So as you can see, my background is very interdisciplinary, and my research vision really is at the intersection between wildfires, the environment, and human health. And I'm really trying to understand how these wildfires impact the environment, especially air and water, but I'm really focusing on water, especially in my PhD. And I'm trying to understand how this environmental exposure caused by wildfires affect human health by causing disease, either infectious disease or non-communicable disease. And as an engineer, we are trying to find solution of this problem of like wildfire impacting the environment and health. And I developed green infrastructure during my PhD to mitigate the impact of wildfires on water. So I want you to keep that research vision in mind if we go into details, which is basically trying to understand again the impact of wildfires on the environment, which is really like, what I've been interested in, and understanding how we can assess the association between the environment and human health. And that's what my talk will be today, is to understand first how the wildfire impact the water. And we're going to look for ocean water and also surface water. And then we're going to see how these environmental changes, the shift environmental caused by wildfires, are going to affect human health by causing disease, by introducing my paper that I'm working on at Stanford here, and then how we can mitigate this impact by using nature-based solutions. And I'm going to also talk about my research, my future research direction. So to start, I think most of you know that climate change is going to make wildfire more frequent, more intense, the United Nations Environment Program released a report in 2022, February 2022, saying that wildfire are going to increase by 50% by the end of the century. And here you can see by a third by 2050. And this is also like some of the front page headlines about wildfires, especially in California. And I think most of you heard about the Los Angeles wildfires. And a study on JAMA has been published in August, showing that it may be linked to 440 deaths, causing especially by by the wildfire smoke, but also by the water and everything. So California has the higher risk of wildfires among all states. When I studied my postdoc in September 2024, I have a plan of a proposal that I submitted for my fellowship. But in January 2025, the LA wildfires happens. It occurs, and I end up being involved in the LA regional wildfire recovery efforts with the Scripps group, which includes LA Public Health Department, also Heal the Bay, the OHIHA, which is the environmental toxicology with the Public Health Department. And I decided to go there in February 2025, so February of this year, and took this picture of the fire because I think most of you know that the Palisade fire was like right on the PCH, and you can see all the burned houses here. And you can see the Eaton fire here. The Palisade fire was, protected by the military, and Eaton fire was not. And you can see on the right side, if you saw some movies, it used to be homes, as you can see where I'm looking right now. It used to be homes, and each home have their private beach, but everything is all gone now. So like Los Angeles is just one example of all the devastating wildfire that happened in California, especially like the tubes or the campfire. And that's really the reason why I was very interested in. So because I was really interested in how wildfire impact, water especially, and it can either impact ocean water and surface water. So during my PhD, I'm mainly focusing on surface water. And the reason is because after a wildfire, heavy rainfall can wash all the burned soils into rivers and streams and potentially contaminating the water and affecting the ecosystem of the water as well. And this is a good example. When I went in LA in February, Monday, Tuesday, Wednesday, the second week of February was perfect. But then on Thursday, we have a heavy rainfall, but that was the first rainfall event, very strong because there is one in end of January, but that one in February was very strong, to the point that, as you can see, there is debris flow that happened on the PCH, and the debris flow has pushed a LA Fire Department car, which was here, to the ocean, because the erosion has pushed and a lot of volumes of debris into the water. And that's really contaminated water. And one of my papers during my PhD showed that wildfire can increase the concentration of pollutants up to 100 times. And wildfire can increase, for example, in water, black carbon, pH, nutrients, heavy metals. We also saw, PCBs and PFAS as well detected in our result I'm going to show later. And then it also has an issue with the drinking water treatment system. And I'm going to show you just right to start after that. But a main result from the paper that I showed during my PhD was that after 1 year, the wildfire pollutants, especially like heavy metals, increase after a year. And that's the main reason is because pH has diluted. And the ash pH is very, very high. And when the pH decreases, it releases the heavy metals because of the solution. And that's a concern because most of the majority of drinking water sources in California are in mountainous region, exactly like the LA wildfires for Palisade fires. And this is an example of the Lake Elsinore wildfire in 2018. And that's an issue because these affect the drinking water sources. And the drinking water sources, while you have the issue of like water treatment pipes are burning during the fire, but there is also the issue of when wildfire increase organic matter in the water source, it can be in contact with chlorine, we know, which is the last step of water treatment system, and the chlorine with the organic matter, which is in excess because of the fire in the water source, may cause carcinogenic disinfection byproduct, DBPs, in the water. And that's why most of the time after the fire, you have a lot of like do not drink water. And that's exactly, especially the case which happened in Maui wildfire to like 2020, sorry, in the Maui wildfires. And that's very a concern because surface water is scarce, and not just in California, but in the world. And we have this issue of wildfire contaminating drinking water in Australia, but also here, you know, in Las Vegas, Nevada, they have to shut down the water treatment system because the water was too turbid, and you cannot treat that water and have these issues of DBPs. And this is also an example in Canada. And this was what, you know, what they're putting in Palisade Fire, do not drink water signs everywhere. And you're supposed to drink a bottle of water after a fire for that reason. And now, this year, I actually I was involved with Heat the Bay to actually analyze how the wildfires has affected the ocean water in LA. So, like I said, I work with Heat the Bay. They collected samples on the January 24 and 28th because it was the first storm event, which was not a very like extreme event in terms of like precipitation, but it was the first storm. So it would be the first flush. And we wanted to see how much contaminants get into the ocean water. And we collected in 10 locations. Paradise Cove and Malaga Cove was used as control sites. But Malaga Cove, I think you heard about the Palos Verdes erosion landslides, has impacted that site, and we decided to use Paradise Cove as a control. And then Surfrider Beach until here, with Water Santa Monica, were contained in the, were included in the burn zone area. And this is, you know, how the water collection look like. And this is physical hazards on the ocean. We collected ocean water here. We were collaborating with UCLA, Ginny J, who is one of my PhD, who was one of my PhD committee member. And you can see the foam here, which is mainly caused because of the firefighter chemicals first check that the LA Fire Department is using, is causing that foam, which means that the ocean was full of nutrients after the fire. And if you can see here, we have heavy metals on the top, turbidity and pH concentration. On the y-axis, you have the concentration. And before and after the rain, basically in January, we noticed that heavy metals increase and turbidity as well increase. We also look for bacteria and nutrients and all the other contaminants. But these are the ones that really shows higher significant difference. And Big Rock has some exception here, but Big Rock has been the site that has the most contaminants, which is a little bit up of the fire. But yeah, if you go there, you can tell. And we also decided to do a time series analysis of the fire by looking how the concentration changed over time. So we have data from January to May. So Heat the Bay collected some samples, and the LA Regional Water Board conducted the monitoring. And we basically, and also co-author on this paper that I'm leading, they're also using, so we're using LA Regional Water Board as well to do this analysis. And as you can notice, so the red point here is February 6th data, and this is February 6th data for nutrients. This example for nutrient, but this is okay for nutrient, heavy metals, pH. We saw that, and suspended solid as well. We saw that trends on all these different group of contaminants because we analyzed for turbidity, pH, PCB, PFAS, heavy metals for the LA wildfires. And what we noticed is that on February 6th, there is a peak of concentration in all of data that was mainly and highly likely due because of the EPA hazardous waste site that was implemented to Topanga on that just some days before we collected the samples. And if you can see here, this is this kind of spatial analysis from north to south location on the x-axis, and the y-axis is the concentration. And Topanga has the highest concentration among all of the burn sampling location, that's the reason we end up having this conclusion about the February 6th. But then we are looking at the ocean water, and I was wondering how much of the burn area, how much of the wildfire really contributed to affect and deteriorate the ocean water quality. And that's why I decided to collect storm drain when I went in February, and I'm collecting storm drain in 5 locations within the burn zone, as you can see here on the map. And my control is Ballona Creek, which is on the south in Culver City, because stormwater really serve as a pathway to carry from burn area to coastal water. And the contaminants contained in the stormwater may explain, like the deterioration of water quality, ocean water quality after the fire. So these are the 5 storm drains that I collected: 2 storm drains, some creeks, 3 creeks, and this is the Ballona Creek water. I think you can see that, there is a lot of debris of the fire from the burn zone, because everything drains from the burn zone into these creeks or storm drain. And we have the results until August. I'm still sending my analysis right now to ICP in Professor Scott Fender's lab at Stanford to analyze the trends until November, because we have been collecting every month right now, and I'm going again in December. But what we notice is that we don't have lead and AG, but we do have an issue with arsenic and chromium at that time. So we noticed that arsenic was kind of high actually for the Ballona Creek control site, but the beryllium and have been very high after the fire, and arsenic as well were very high after the fire. Now we can notice a trend of like increasing of metals in August, but I need to see the trend after August if like the metals are increasing or decreasing basically. And to understand the health, so now I've presented like how wildfire affect the environmental cause environmental exposure by air and water, and especially water. But here, when we know that environmental is affected by air and water, I was wondering how these environmental changes may cause human disease, especially infectious disease or non-communicable disease. But I'm in the School of Medicine in infectious disease, and I never heard about wildfires infectious disease that much. So I decided to do a review paper on like how wildfire increase infectious disease. And we screened 2,000, I did a search term with wildfire on the one side, not specific on air, but wildfire on the one side, and the other side of the search term is everything infectious disease related. We found 2,000, we didn't find, we screened 2,500 abstracts, and we include 134, like in the included studies, only 134 studies. Among these 134 studies, there is 76, which is very, like, they mention general, like, respiratory disease, including infectious disease, but that's in that they use the International Classification of Disease and say it's ICD-9 J0099, which includes pneumonia, for example, or like influenza or acute bronchitis, but that doesn't specifically talk about infectious disease itself, the paper. There is also like wildfire cause disease, death, and even premature death. And there is 7 studies that show that. But the paper that really like talk about specifically on infectious disease and that look at into infectious disease specifically are 39 studies. Among the 134 studies, we have 65 studies that come from US, 19 from Australia, 18 from Brazil, 8 from Canada, and Southeast Asia. The rest is remaining from Southeast Asia. And if you look at the number of studies of the 134 study in US, you can see that 24 coming from California, and then 5 in Colorado, Washington, North Carolina. Like I said, if you're only looking though at specifically on warfarin disease studies, the 39 study I'm saying, because this is for the 164 studies. But if you're only looking for 39 studies, you have 27 studies that is in US that really talks about infectious disease and look for really like specific infectious disease. 1 in Canada, 4 in Australia, and 3 in Brazil. And as you can see, very few, like some in Southeast Asia, 13 in California, actually. I forgot to mention that, but there is 13. So majority of papers are coming from California. And very few in other countries, especially low middle income countries. And in this paper, they assess exposure by using PM 2.5, or a little bit older paper use PM 10 to assess the exposure. And I think you can see the picture here, how small is PM 2.5. And this is a hair, this is a beach sand, and this is how PM 2.5 is very small. So paper have been using wildfire exposure using PM 2.5 data. And also, they also take some gas as well as a measurement. And the outcome that we find, the main results of the paper is that wildfire increase fungi, bacteria, and viral infectious disease. So fungi include coccidioidomycosis, aspergillosis. Viruses include influenza, SARS-CoV-2, especially of COVID-19, a lot of paper on COVID-19. And bacteria include pneumonia, tuberculosis, and also you also have upper respiratory tract infection, acute bronchitis as the main outcomes. So here you can see the association between wildfires and human health effects, which means, like, for example, if you increase 1 milligram per cubic meter of PM 2.5, you may have an increased risk of COVID-19 of 0.4%. So basically, this is a risk, and this is the exposure, like how much, if you increase of this exposure to yourself, like to human health, how much it will cause in your body. Or it may cause you actually also to go to hospital. It may also have a risk to actually to death. And the main highlight of this paper for me, it was like the lack of daily PM 2.5 data. Like I said, in low middle income country. For example, I was born in Madagascar. And when sometimes I look at the NASA, which is here, the NASA satellite for active burns, there is usually a lot of burning. Red dot means burning. And you can see the AQI, which is like the measurement of PM 2.5, which has 1 in Madagascar, because I know about it, 1 in Madagascar, and like very few in Africa and the other low middle income countries. And that's the reason why there is not that much study, because if you don't have assessment of exposure in this country, you cannot really make the association of warfare and disease. And the explanation of like why warfare can increase infectious disease is because warfare decrease immune system, increase inflammation, increase also oxidative stress, which make you more likely to have infectious disease. Also, warfare, because of deforestation, can cause deforestation that may increase actually cases of malaria, but that is more like indirect effect. And coccidioidomycosis, which is the only one which is, I would say, like fungi, infectious disease, is because when there is a wildfire, the soil is disturbed, and these small coccidies are in the soil, and when they're disturbed by the wildfire, the spores get into the air, and you can breathe that and get sick. So that shows how warfare affects the human health. And then we wanted to understand if there is a way to disrupt, this pathway of exposure to human health, especially for water. And that's why I did my PhD. We wanted to know how green infrastructure can mitigate this impact. My study actually demonstrated that warfare green infrastructure are resilient for like physical, chemical, and biological functions. So that means they can effectively remove it. And that's the case for heavy metals, for example, because the data show that the wet fire residue did not affect the removal of capacity of the biofilters here. And this is heavy metals. The removal didn't change that much. And then I also developed a novel biofilter media by using drinking water treatment residuals to increase the removal of these biofilters to remove phosphate, because phosphate was not removed very well. And by adding, like drinking water treatment residuals, it removes well, and which is an issue because, PhosCheck, which is LA Fire Department in California, we use PhosCheck, which is a phosphate ammonium-based firefighting chemicals. So to conclude, if you look at the research gap that I was showing you, if you look at, how wet fire affects the environment, we can quickly see that there is not that much study that shows the association between these environmental changes, environmental exposure caused by wet fires and human health. So we need more study, especially epidemiology studies, that shows the association between environment affected by wet fires and human health. And also we noticed during the LA wildfires that there is no established human health risk threshold, even though I'm working with the head of the toxicology department with, LA Public Health Department, to really say at this level, you may be at risk, for cancer or like chronic disease. And so that's why I wanted to, again, show the emphasis that we need to do more studies on infectious disease and air especially, and also on water. We know that link between wet fire environment and water, but we don't know that link about how water may actually affect infectious disease and non-communicable disease, and that's my future research plan. And also like the long-term exposure, which is non-communicable disease. For example, the surfers, after the fire, they goes into the water and they get exposed to those contaminants that I've been mentioning, heavy metals, PCB, PAH. And then long-term, if they go frequently into the water, they may have a high chance, of getting cancer. And that's something that we want to pursue with AEESP and Jade Benjamin Chung in the School of Medicine to see, if this community warfare can have chronic exposure. And finally, the monitoring, we need to improve monitoring of PM 2.5 because that will help us to have more studies on wildfires and human health. So these are references, and also my 3 papers that I'm currently working on, and one of them will be submitted in January because one of these papers will be the 1-year anniversary of the LA wildfires. We want to do a press release with the NGO. So that's why we're submitting this paper. And I want to acknowledge Dr. Jason Andrew Lab, the King Center, which is sponsoring me, and also Dr. Mohanty Lab from UCLA. Thank you.
Thank you so much for this great talk. We have some time for some questions from the audience. Go ahead, Dr. Wang.
Thank you. Thank you, Anja, for a great talk. Curious about your first part where you mentioned after the wildfire, just due to the contaminants, don't drink the tap water, right? Actually, we just experienced a very similar thing at West Campus in this week. Everyone's notified do not drink tap water because some E. coli detection somewhere on the campus location. So I'm curious, after the wildfire, for the change of the microbes and the pathogens in their community, did your study only look into that part?
I did not look into warfare and especially bacteria.
Microbes.
And E. coli. We have a team at UCLA who are looking at that actually, how warfare increase bacterial level, E. coli. And Heather Bay, which is the NGO I'm working with, are doing that work specifically on that. So but my next step also as a future faculty, hopefully, is to also understand how warfare can increase pathogen in water. Because if warfare increase pathogen in water, microbes, not all microbes are bad. If the microbes cause disease, it will be pathogen, and these pathogens may cause infectious disease. And that's the plan I proposed to the King Center actually, before the LA wildfires happened. But that was my plan, to show that because, because the water is so turbid, there is less sunlight, for example, that goes into the water, sunlight and UV, or like a disinfectant. And if there is less UV that kills the pathogens in the water, it is more likely to be a pathogen source to the people. So people get exposed to that. And that's what I wanted to look for. And I'm planning to do it. I'm still planning to do that. It's just like in the near future after the LA warfares gets resolved. But yeah, that's definitely something we want to pursue. I really want to pursue that. But yeah, we usually look at E. coli, fecal coliform as well. But we never saw the link between, like water and infectious disease. So that's a research gap as well.
Thank you.
Thank you for your question.
Yes, go ahead, Jeffrey.
Is my audio okay? Can you hear me?
Yeah.
Okay, great. My audio on this computer doesn't always work, so good news. It's nice to see you. Thanks for a nice talk. You at the end you had this image of the plane with the firefighting chemicals, and I'm curious, what chemicals are used to fight fires at this scale, right? Like a small scale, a burning house in an urban setting. I guess that's where we use firefighting foams, and we have problems with PFAS long term. What happens with these large scale fires? What chemicals do we use, and what sort of lifetimes do those chemicals have in the environment? And are we going to have sort of legacy contamination issues with the application of these firefighting chemicals?
That's a good question. I know, like even recently, the LA Fire Department have been using PhosCheck actually, which is the red, like the red thing that could drops from the fly. But they have been using PhosCheck. I told you it's a phosphate ammonium based. They use it. They don't put everything where there is the fire, but you usually put it around the area of the zones, and that's the reason also firefighters get coxomycosis, because they're preparing the soil, removing the vegetation, so that PhosCheck, like the firefighting chemicals, get deep into the soil, and then when you put that PhosCheck around the burn zone, it will contain the fire and stop the fire spread, if that makes sense. So that's what they're using. Even at large scale, they're using that PhosCheck to just contain the fire and stop the fire spread. But yeah, there is this issue with phosphate. Like phosphate, I told you, like if you just saw the picture, like on my talk, when we collected in January, like there is the foam, and we all know that the foam was coming because of high concentration of nutrients. At that time, there is not the algae bloom, so we're 100% sure that it was not because of algae bloom issue that we have in LA some month after, but that was mainly because of that. And we also have the same issue. So in the PCH drain area, where we know that the firefighter put that, like the PhosCheck there, we have high concentration of nutrients in these specific locations. And PFAS is also an issue. I was planning to do that during my PhD, and then I emailed the LA Fire Department about that, because I buy the PhosCheck, what they're using, and they are trying to avoid the question about PFAS, because my, like Professor Sanjay Mohanty is also doing PFAS work. So yeah, definitely that's something we need to pursue and look for it, because long-term water is affected by these firefighting chemicals. I know Professor Pat Abdel, he is in Stanford. He is looking for like green firefighting chemicals, actually, like not using PhosCheck. So yeah, trying to find solutions for the more environmental friendly. But thank you for your question. It's good to see you.
Thank you.
All right, that brings us to the end. So thank you again to both of our speakers. This closes out the Future Faculty Seminar Series. This and all other seminars are posted to the AEESP YouTube page, so be sure to check those out. And enjoy the rest of your Friday and your weekend. All right, thank you.
Thank you so much. Thank you.
Thank you. Good to see everyone. Bye.
Yeah.
Bye.
Bye.